Okay, so I'm going to talk about making a state of equilibrium and the equilibrant force. So we're going to go on the last problem that we did on concurrent forces. So if you haven't watched that video, you might want to watch that one first. But we're going to take two forces that are concurrently working. So we're going to have a force going this way and another force going something like this. And we're going to say this is a 10 Newton force. And then we're going to say this is a 15 Newton force. And we're going to say there's 20 degrees between them. And so we see that we have a force going up here and a force going this way, and we can figure out what the resultant force is. But the overall problem here is I'm going to try to figure out what is the third force that I could add. Where should I add a third force on this point right here? These are concurrent forces work on this point. Where would I add a third force on here so that this whole thing is an equilibrium? And equilibrium means that there is, it's very important to know what equilibrium means. It means no net force. There is no leftover force at all. And if there is no force, we know Newton's second law is F equals ma. So if there is zero net force, there is zero acceleration. So we want to make sure that this object is not accelerating. It doesn't mean it's not moving. It could be moving along at a constant velocity, but if there is zero net force, it will not be accelerating. Right now, you can see that we're kind of pulling it up this way and over this way. So clearly, it's going to be there's going to be a net force somewhere up in this direction, and therefore it's going to be accelerating. We want to figure out what is the third force I could put on here that would be what we call the equilibrant force. The equilibrant force. The force that would, if added, would bring this into equilibrium and therefore would not have it be accelerating. So the way to do this is to first just figure out your resultant force between these two. So we're going to do that first. So I'm going to take this 10 Newton force and we're going to add it on right over here like this. And if I draw a little dotted line out here, I know that this is 20. If you remember, we did this in the last video. So this in here in the middle is 160 degrees. And I can then figure out a resultant force from the tail of the first to the head of the last, just like this. There's my resultant. And I can use, I can either do I hat, j hat, or I can just use, since I've drawn it this way, I'll use just the law of cosines. So I know I have 15 squared plus, this was 10 newtons here, by the way, plus 10 squared minus 2 times 15 times 10 times the cosine of the angle in the middle, which is 160, and I can take the square root of that whole thing, and if I do that, I get a resultant vector of, if you do it in your calculator, you get 24.6 newtons, and I want to figure out which way this vector is pointing. So I want to figure out, probably this angle right in here. And to figure out this angle right here, theta, a lot of times we'll use the law of sines. It's a nice easy ratio of the sine of an angle over its opposite side. So the sine of that particular angle over its opposite side, which was 10, should equal the sine of another angle in the triangle, and we'll use that 160 because that's the only one we know, sine of 160, over the opposite side, which we just figured out, 24.6 newtons. So I can take sine of 160 times 10 and divide it by 24.6, and then I'll take the inverse sine, and I will end up getting an angle of about 8 degrees. And so the resultant force is going to be 24.6 newtons at 8 degrees north of east. 8 degrees north of east. Another way, that's right here. Another way to write this, because if I have a grid on here, instead of writing 8 degrees north of east, I can measure from north all the way around to this. So that would be 24.6 newtons at 82 degrees. And all I have to do is just write degrees. And we did all this in the last thing. But what the little difference that we're doing in this one is we're trying to figure out what is a third force that I could add to this that would bring these other two yellow forces into equilibrium. Well, these two yellow forces working together are this blue force right here. That is the resultant force. So right now, this object will be accelerating in that direction. If I want to bring this into equilibrium so that there is zero acceleration, I need another force that is equal in magnitude to this force, but completely opposite in direction. So I need to take this exact same force, and I'm going to add it on, going off in the other direction. And it'll be a little bit longer than that, and it should be going along straight, perfectly straight with that force. So the equilibrant force, the force that could be added to bring everything into equilibrium, is always going to be equal and opposite to the resultant force of the other forces. So no matter how many forces I have, if I figure out the resultant force of all of them, then the equilibrant force will be the force that's equal and opposite to that force. So this right here is what we call the resultant. The equilibrant would be 24.6 newtons also, but it'd be going all the way around in the opposite direction. And so if we wrote at 82 degrees, all we'd have to do is we'd say 24.6 newtons at, and we just add 180 degrees to this. So instead of going to 82, we're going to add 180 degrees more on, so that we're going to be going in a more of a, and that, I didn't draw that very well, it should be more straight right along that way, opposite from this resultant force. 24.6 newtons at, it'd be 262 degrees. 262 degrees. Or you could say 8 degrees south of west. If this was 8 degrees north of east, my equilibrant force would be 24.6 newtons at 8 degrees south of west, this degree here. It's easier just to go from north and just add 180 degrees onto it. But so this vector, or this movie, along with the last movie, hopefully will make sense, because all we've done differently here is we've figured out the resultant in the last movie, and we're trying to figure out what would be the equilibrant force. What would bring this into equilibrium so there's no net force, which means no acceleration. And it is simply the same magnitude of the resultant, but in the complete opposite direction, and that will bring everything into equilibrium. So hopefully that made sense with the equilibrant force and equilibrium.